So first of all, thanks to the Functional Knots folks for putting this together, and for my Christian brothers and sisters, blessed Good Friday. I put Reed on the spot, as you observed this morning, because all I told him was, I'm not going to talk about functional programming. So here I am, not talking about functional programming. I need a launching off point. So my metaphysical stance comes from Nobel Physics laureate Steven Weinberg. The problem is not that we take our theories too seriously, it's that we don't take them seriously enough. I'm going to stick a whole bunch of ontological stakes in the ground here. I only have 45 minutes. If Emily thought she had a lot to cover in 45 minutes, I'm kind of like taking that to the next level. This is going to be even more kind of all over the map than most of my presentations, which are already pretty all over the map. So A, please bear with me, and B, the reason I'm last is so we can have a lot of time afterwards, to ask questions and cover whatever people might want to cover. Okay, what do we mean by computing? And this is a question that sort of came to a head at this point in 1936. Alan Turing famously tries to come up with an answer to a challenge that was issued by a German mathematician named David Hilbert called the Entscheidungsproblem, for those who speak German and even for those who don't speak German, because I have no idea what that translates to. But actually I'm lying, I do speak German and I do know what it translates to. It's the ending problem. The halting problem, some of you may have heard of it under that name. So Hilbert wanted an answer to the question. He posed a list of questions for mathematicians to try to answer. And part of the problem was we didn't really know what we meant by computing. Remember, this is 1936. So there's no such thing as a digital computer at this point. And in fact, the mathematical community itself is not entirely sure what they're doing or how they're doing it. And so this question is actually tackled by several different people. It's tackled by Alonzo Church, the lambda calculus. It's tackled by Alan Turing with the Turing machine. And it's tackled by a logician by the name of Kurt Gödel, who comes up with a system called recursive function theory. And remember, now you're thinking, oh, recursion functions, okay, that's what we're all here to talk about. No, it's not. At least not at the time that Kurt Gödel was coming up with this stuff. But anyway, our friend Alan Turing here comes up with a description of an idea, a theory, a concept, as to what we might mean when we say we are solving a problem, we are computing something, we are calculating something. And that's again, 1936, it's anything that can be computed, right. Yeah, it's interesting because actually Gödel and Church got there first and they talked to each other about it. Gödel thought his recursive function theory could compute anything that could be computed. Church thought his lambda calculus could compute anything that could be computed. They weren't sure. And so they talked to each other about their respective systems. Do they both express the same thing at the end of the day? Are they equivalent in expressive power? And actually, when Church explained to Gödel that he thought their systems were equivalent, that didn't cause Gödel to agree. That actually caused Gödel to doubt that his own system was correct. And if you know anything about Kurt Gödel, you can imagine how difficult it was to convince Kurt Gödel that he was wrong. But anyway, along comes Turing with his Turing machine, and that finally not only convinces Gödel that his system is correct, but it convinces him that all three are actual successful descriptions of how to compute anything that can be computed at all. Okay, 1936. There was a lot going on in the world in 1936, and for probably 50, 60, 70 years prior to that. The reason anybody's asking what does it mean to compute anything is because of something Emily talked about, which is this brilliant Russian-German mathematician Georg Cantor, who had come up with this infinite set theory to try to serve as a foundation for all of mathematics. Like anything you can talk about in mathematics, you can talk about in terms of this infinite set theory. And that was at the end of the 19th century. And his motivation, well, actually, I don't know what his motivation was. But one thing he wanted to be able to express anything that was true in mathematics. That was kind of a big deal at that time. One of the reasons for that is because of the success of physics. For that, we have to go, I'm going to put in a bunch of stuff with some extra slides here because I think it's important, given the conversations we've had so far, it's important to understand why this question was being asked. Bear with me, I'm going to spend a lot more time on this slide than any of the others, probably. Because I have to go back to the 17th century. I have to go back to Newton. And people don't really understand, I think, they don't really appreciate what a paradigm shift it was when Newton said, first of all, you can use mathematics to describe reality. Okay? Believe it or not, that was not a generally understood, accepted principle by the 17th century when Newton sat down and said, yeah, actually, we can describe motion, we can describe how things interact in the physical world with each other, and by the way, we can do it all with relatively simple equations. The only problem is we have to invent new mathematics. Minor detail, right? So he goes off and invents the calculus at the same time that Gottfried Leibniz does. And there's a big debate about who got there first and all that kind of stuff. But anyway, the main point is that mathematics is connected to physical reality. Okay? And that's an explicit goal that Newton established, and then established how to do it, and then did it. Okay? And in fact, you can hop on Amazon right now, and you can buy a brand new translation from, I think, 2013 of the Principia Mathematica. It was written in Latin because you had to write in Latin if you wanted to talk to educated people in the 17th century. So that's been translated into English again. It's been translated in English multiple times, but this one's a particularly good translation. It's nice and new and modern. I recommend it. Okay, so mathematics describes the physical world. Fast forward, there are problems with the calculus that Newton comes up with. Sometimes you get nonsense results out of it. In other words, you get results that don't actually describe physical reality, or you just don't get any results at all. You get infinities and nonsense and, all this. There are no infinities in the real world. There are, nobody's ever measured an infinity in the lab. Okay? So there are these interesting philosophical questions about the relationship between math and the physical world. And there are inconsistencies in the original calculus of Leibniz and Newton. Fast forward a couple hundred years to the 19th century, and you get to the end of it, and a couple of important things happen. First of all, several important things happen. First of all, a couple of other mathematicians solidify the logical foundations of calculus, and that's where you get this subject that some of you had in school called real analysis. Right? And you heard names like Weierstrass and Cauchy. And so now there's this rigorous epsilon delta proofs and all this kind of stuff. So calculus is put on a pretty rigorous logical foundation. A couple of other physicists, Hamilton and Lagrange, say the problem with Newton is you have to deal literally particle by particle. That's ridiculous. That's not practical. You want to be able to talk about whole bodies at once. And so they come up with math to do that. And I'll talk a little bit more about Hamilton and some of the stuff that he contributed later. But anyway, along comes Cantor, and he comes up with this foundation for all of mathematics. The only problem is it talks about infinities like they're real, and it talks about infinities like you can compare them, and some infinities are larger than the other, like Emily said, and all this kind of stuff. And there was a violent reaction to this because it was so disconnected from the physical world. And that might sound weird to talk about concerns about mathematics being disconnected from the physical world. I mean, isn't it? No, it hadn't been up to that point. And so Hilbert started doing stuff like, there was a problem called Gordon's problem, which had proofs at sort of low sizes of values of the problem. And the challenge was to do it for bigger sizes of data put into the problem. And Hilbert decided he would do it with this new style of mathematics that Cantor came up with. And so he came up with a proof for a larger version of this problem. Paul Gordon came up with this problem, showed it to Paul Gordon, and Paul Gordon famously said, "Das ist nicht Mathematik, das ist Theologie." I don't think you have to speak German to translate that. This is not mathematics, this is theology. And it was, actually. Cantor's motivation, I said I didn't know what Cantor's motivation was, I lied again. Cantor wanted to know the mind of God, and he, in fact, believed that God had revealed transfinite arithmetic to him. He sincerely believed that. He was a very devout person. So was Newton, by the way. If you pick up the Principia Mathematica and read it, not only will you find the invention of the calculus and Newtonian physics, you'll find Newton's design argument for the existence of God, because Newton believed that God created an ordered universe, and that's where we got Newtonian physics in the first place. Okay, so Cantor is talking about all this infinity stuff, and this infinity is bigger than that infinity, and yuck, 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 yuck. And traditional mathematicians are going, you're literally out of your mind. Like, this isn't mathematics, this is outrageous, this is not what we do. This is not how we do what we do. Well, that of course begs the question, how do you do what you do, right? And so that was one of the things that Alan Turing was trying to answer, and Church invented his lambda calculus in response to another Principia Mathematica, the Principia Mathematica of Bertrand Russell and Alfred North Whitehead. So there was a lot going on at this point in the beginning of the 20th century, the 1930s. Okay, now I had better move on, or we will in fact be here all night. Okay, this is where I have to try hard not to cry, because I've been here. This is Bletchley Park, 51 miles northwest of London. It was established by MI6, James Bond. Okay, not James Bond, but James Bond's boss. No, not M, but the real one. MI6 bought this essentially ranch, essentially farmhouse, and several acres of land around it, 51 miles northwest of London, for two reasons. Because it's equidistant between Oxford and Cambridge universities, and because there's a train station right there. This is handy because you're not going to get bombed out of existence when the Nazis start dropping bombs, which, by the way, they do very shortly thereafter. You can recruit people from both Oxford and Cambridge and have them get on a train and get there. Okay. So they set this up as the code and cipher school, the government code and cipher school. So this is where basically everything that has to do with breaking codes is going to happen. It's going to happen at Bletchley Park. And this is happening, when did we buy it? I forget. Yeah, 1938. Right. So Turing publishes his important paper in 1938. MI6 buys Bletchley Park in 1938. And then they go looking around for people that they might want to help them break codes. And what is Alan Turing talking about? How it is we calculated or compute anything, right? So not being stupid people, apparently at the top of the military intelligence command in MI6, they say, let's bring in Turing, right? So that happens. Turing literally trains in cryptography for the rest of 1938, shows up the day after war is declared in 1939 at Bletchley Park. How do you break codes, right? Oops. Helps if I actually go on to the next slide, doesn't it? Okay. How do you break codes? Guess. The most important thing you can do in breaking codes is guess the message well. Okay? In order to do that, it helps to know the language that the plain text is written in, and it helps to know what domain it's talking about, right? So here we have an example, of course, from Wheel of Fortune, and it probably helps to know, as they point out here, that we're talking about some sort of food item, and of course we all know the language is English, right? Okay. So given that, you might be able to, with a few moments thought, figure out what that message is, right? And that's basically how code breaking works. So this is the sort of thing that Alan Turing and crew are working on at Bletchley Park. Except they're doing it with a vicious German cipher machine called Enigma that's a polyalphabetic substitution cipher with 6 wheels. And the positions of those wheels change every day. So there are hundreds of millions or hundreds of billions, I don't even remember, possible combinations of this already very complex polyalphabetic substitution cipher. And the problem is that even if you get through part of an encrypted message that the Nazis are sending around to each other, you're not going to get the whole thing all at once. You're going to wind up with something more like that Wheel of Fortune board, where you've got a letter here, you've got a letter there, you think, right? You haven't completely decrypted the thing, so you can't just pick up your German, English, English, German dictionary and go, yeah, that's it. So you have to have some notion of how much information you've extracted from this encrypted message. Well, okay, what do we mean by information? How do you measure information, right? What sort of metric? I mean, we're mathematicians, all these people are mathematicians and chess players and all sorts of that, that's logicians, that sort of thing. So how do we measure information? Turing, bright guy that he is, comes up with this notion of how to measure information. How much information do we think? It's a probabilistic concept. How much information do we believe we've extracted from this message? And he comes up with a unit for it. He comes up with a unit called the band, which is the amount of information that changes the probability of one result versus another by 10%, 1 in 10, right? And so they start to apply this, and they come up with a methodology for cracking the Enigma code that as they make incremental progress on any given message with this machine, which they have to invent, right? That's the part that's more famous, really. They invented this code-breaking machine called the bomb, B-O-M-B-E. Very fascinating. But that's not what I'm here to talk about. They come up with this measure for information. And that's another breakthrough. And I'll argue that's a more important breakthrough, ultimately, even than the fact that they cracked the Enigma code eventually. Okay. All right, moving on. Information becomes rigorous, yeah. Claude Elwood Shannon, okay, works at Bell Labs. He works in switching circuits for the Bell Telephone Company and Bell Labs. So how do you route calls from one point to another? This is all becoming automated, unfortunately putting a lot of switchboard operators out of work, but that's all part and parcel of this sort of era of progress. So he comes up with a mathematical theory of communication where he's talking about circuits, he's talking about electrical circuits, he's talking about the phone, right? You pick up the phone and you can you send a message, voice or otherwise, to somebody else, and that line can be noisy, and it can be so noisy, especially when it's on radio and it's wartime and all this kind of stuff, that it's really, really hard to make out the message. And so how can we, first of all, what are the properties of a communication channel? What are the mathematical properties of a communication channel? And once again, what do we even mean by information, right? And so Shannon, independently of Turing, comes up with a measure, he comes up with this thing that measures how much information you need in order to distinguish between two equally probable messages, possible messages, two equally probable messages. Only two are possible. The two are equally probable. How much information does it take to distinguish between two equally probably likely outcomes? 1. What is the unit of measure of that? 1. It's called a bit, right? You probably didn't know that, and I think this is criminal. You think bit means binary digit. Well, it does. But that's not where it came from. It didn't come from this notion of on, off, not yet. It didn't come from this notion of on or off. It came from World War II, and how do you measure how much information it takes to tell whether you got to launch the missiles or don't launch the missiles, right? It is a measure of information first. It so happens that it's representable easily as a 1 or a 0, an on or an off. And yeah, that comes from Shannon too, because guess what? He works for Bell Labs, right? He's dealing with a bunch of relays, literal physical relays, little things where there are contacts above and below a lever, and the lever goes up or down, and it makes contact or doesn't make contact. That's how you used to do things before there were transistors, right? That's how you used to do circuitry, and in fact, one of Shannon's major contributions, his master's thesis, is about this algebra of logic a 19th century algebra of logic, and how to implement this algebra of logic with relays, on, off. Might take hundreds of them, but how do you implement this algebra of logic? What algebra of logic is that? It was invented by a guy by the name of George Boole, right? Anybody heard of Boole here? Come on, all your hands, come on. Right? Yeah, that George Boole, right? So he came up with an algebra of logic, Boolean algebra, right? That had never been implemented in any way, shape, or form other than pencil and paper, until Shannon, working at Bell Labs, said, hey, I think I can do that with these relay thingies that go on or off. And that's how you get AND gates and OR gates and NOR gates and NOT gates and all those gates, all of them. Didn't exist until Claude Shannon created them. By the way, Claude Shannon collaborated with Alan Turing on an unbreakable phone system in 1948. Again, went over to England, and they created a system called Snively. It's an unbreakable encrypted phone system in the late 1940s. And this is an awesome thing because it lets Churchill and Roosevelt, I think, at the time, talk securely, and other folks too. Very interesting though. The Snively system in England was installed not at wherever the main British political offices are, 10 Downing. It's installed in the basement of an American retail store, Selfridges. Partially because Selfridge is a major American patriot and wants to help. Partially because it's a lot more secret, and then going, yeah, let's take our encrypted phone system and install it in the most obvious place in London. And also because Selfridges was strategically located across the street from the US Embassy. So whenever Churchill wanted to have a secure conversation with Roosevelt, he could just go shopping. Right? And go down, I'm serious, he would go shopping at Selfridges, which is a hugely famous store in England, even though it's an American store. By the way, Churchill was half American. His mother was American. That's another historical fact that a lot of people don't know. Anyway, he could go down into the basement of Selfridges, pick up the phone, talk to Roosevelt, and then walk across the street to the US Embassy to talk to the ambassador with information that he had that he couldn't have gotten any other way, securely, right? So, very important figure, Claude Shannon here. And Shannon comes up with the field of information theory. He comes up with this measure of information, formalizes it, and we can even talk about it digitally, which is, very, very novel at that point. Oh, I forgot the most important part, sorry. So he comes up with these equations to describe information or the lack thereof, right? And the lack thereof, he needed a name for the uncertainty in what message you were going to get over one of these communication channels. He didn't know what to call it. So he talked to another really important figure by the name of John von Neumann. Have anybody here heard of the von Neumann architecture? Yeah, you're all using it, right? All your hands should be up. The von Neumann bottleneck, the von Neumann architecture. Every CPU in the world, to a first approximation, is a von Neumann architecture. Okay, anyway, so he talks to John von Neumann and he says, what should I call this uncertainty about which possible message you're going to get? Von Neumann says, well, why don't you call it entropy? Because it's a term from thermodynamics and nobody knows what it means, so anytime you use it, nobody will be able to argue with you. It's literally what he says. And so there's an analogy as far as von Neumann and Shannon are concerned between thermodynamic entropy, the fact that in physics things tend to go to hell in a handbasket over time, the heat death of the universe ultimately and all that, and this notion of we don't know, there's uncertainty as to which message of multiple that could happen is going to come over this channel. It's entropy as far as information theory is concerned. And Shannon goes, okay, fine, I'll call it entropy, because also mathematically the equations are very similar. They're so similar, in fact, that a physics grad student at the Information for Advanced Studies at Princeton, New Jersey, says it's not an analogy. Okay? Ed James, E.T. James, is a grad student brought to the Institute for Advanced Studies at Princeton by J. Robert Oppenheimer, right? Father of the atomic bomb. And his background is statistical mechanics. He deals with gases and liquids and pressures and the fact that you can't know how fast all those molecules are moving. You can't know how many of them there are in this gas tank and all that sort of stuff. So you have statistical mechanics. It's all about probability. It's all about statistics. And Jaynes reads Shannon's 1948 paper and literally goes, as he reports himself, literally goes running around the halls of the Institute for Advanced Study at Princeton, New Jersey, showing it, as he put it, to anybody who would listen and a number of people who wouldn't. And it changes his worldview of his subject, which is physics. It changes his worldview of his subject, which is statistical mechanics. Because, especially also now, this is obviously well after the 1930s, so quantum mechanics is a thing. And in statistical mechanics and quantum mechanics, we talk about randomness. We talk about the fact that these processes, you can't know exactly what's going on in these processes. And there's a philosophical question here as to whether there's real randomness in these processes, or it's just you can't know. The processes are perfectly deterministic, they're perfectly reasonably behaved, but because there's so many molecules and they're moving so fast or what have you, you just can't know where they are or how fast they're moving. And of course in quantum mechanics that shows up as Heisenberg's uncertainty principle, and that's another sidebar we could talk about all night, or at least I could, but I'm not going to. But Jaynes looks at this and says, okay, there's now a mathematical theory of reasoning under uncertainty. What he does is he connects the dots from probability theory to information theory as articulated by Shannon. And so that's an amazing thing to say. There's this intuitive notion of probability that people have been working with for a very long time up to that point. And Jaynes goes, oh my gosh, first of all, in physics, when we say we're talking about randomness, we're really not. We're really talking about missing information. That's his major stance. And then he starts developing or evolving probability theory based on information theory, but in order to make it work, he has to adopt a pre-Cantor approach to mathematics. He has to approach, and I've got a list of names here, right? Let's see. Gauss, Kronecker, Poincaré, Bauer, and Weil. Okay, these are all, to sum up, these are all very traditional pre-Cantor, except for Weil, who was a critic of Cantor's, contemporary with Cantor. They all basically said, this guy's nuts. This transfinite arithmetic, infinite set theory thing is nonsense, and we shouldn't use it. Well, why not? What's wrong with classical math? And I won't read that entire slide to you. I apologize for the wall of text. You can look at it offline. But basically, there's this theorem in topology. Okay. Yeah, a little bit of a sidebar. Topology is the study of continuous surfaces and how they change shape without tearing, without violating their structure, right? Without poking a hole in them. So that's topology. There's a theorem in topology, as it is understood to this very day. Okay, this is going to sound ridiculous. Why? Because it is ridiculous. It's called the Banach-Tarski paradox, and it basically says you can take a ball. A ball is a solid sphere. You can take a ball, you can carve it up into a finite number of small pieces, chop it up, and you can rotate those pieces and put any two of them back together again so that they have the same volume. You come up with a ball that has the same volume as the original ball, right? So you have a ball, let's say you have a ball whose volume is, a quart. You chop it up into 6 pieces or whatever. You take 2 of them, you rotate them in this special way, and you put those 2 pieces back together and you get another quart ball. Okay? Like I said, if that sounds ridiculous, it's because it is ridiculous. Your intuition about that is perfectly fine. It violates the conservation of matter in physics. Okay? It's nonsense on stilts. But you can prove it in classical topology. And the proof involves these epsilon deltas and the calculus, the formal, the rigorous, the good calculus that came up at the end of the 19th century. It's a perfectly good theorem in that logic. Back to Emily's point about there being more than one kind of logic. in classical logic, in classical point set topology, Mengenlehre. Okay? Hausdorff, called it Mengenlehre. Poincaré said Mengenlehre is a disease from which future generations will be said to have recovered. So we're all tied up in this mess, and James is saying, if you put probability and information theory together, and you stick to if you stick to the old, this is a counter-revolution. If you stick to the old style of traditional math from the 19th century before Cantor, things make sense. You don't get nonsense. Okay? Super important as far as change is concerned. Yeah, I already basically covered this. Isn't math math? Isn't logic logic? This is a Dutch gentleman whose name I will not pronounce correctly because I can't pronounce Dutch names correctly. Brouwer is as good as I'm going to get. So his program, he is the main figure in this constructivist or intuitionistic approach to mathematics. And that basically boils down, it's very simple, it boils down to a couple of things. One is, it's taken in classical logic that either a proposition P is true or that same proposition P is not true. P or not P is considered a fundamental axiom of classical logic. Everything is either true or false. And intuitionism or constructivism rejects that idea. And this is very interesting. It's like, why on earth? I mean, isn't that obvious? Isn't it obvious that every proposition is either true or not true? Well, in a sense. But the argument that I'm going to make, and as far as I know, this is original with me, is that the constructivist argument is you can't pretend to have information you don't have, in the information theory sense, in Shannon's information theory sense. And the closest I've gotten to seeing this in any other text is in this second quote from Paul Taylor, which I really like. That this is called the law of the excluded middle in classical logic, by the way, P or not P. And Paul Taylor says, it seems obvious, the law of excluded middle seems obvious, until you think about the reasons for believing it and see that it begs the question, because it assumes omniscience. It assumes you know for a fact that either proposition P is true or proposition P is false. It assumes omniscience, a knowledge that no other science would claim. So throw that away, and throw away anything that follows from it. So for example, if you scrub your cobwebs in your brain a bit, you may remember back to geometry class, you may remember actually having to do some proofs in geometry. And a very popular approach to those proofs was to start by assuming that what you wanted to prove was false. And then going step by step by step by step until you get to the conclusion, and the conclusion is a contradiction to your original premise. So in other words, it's a contradiction for the premise to be false, which is another way of saying double negation, not P implies P, right, for proposition P. So without the law of excluded middle, you can't get there either. You can't say not P implies P. Truth or provability is not the same as saying it's a contradiction for something to be false. You have to actually go step by step by step and say, yeah, here's the process by which we arrive at this conclusion, not I'm going to assume the conclusion is false and then I'm going to justify the conclusion that it's false. Okay, so that was Brouwer's big thing. How does this relate to the work that Turing did on talking about what we even mean by thinking or computing or calculating in the first place? And here's a direct quote from Turing's, well actually it's not a direct quote from Turing. It's a quote from Phil Wadler's Propositions as Types paper, which I also highly recommend everybody read. And basically what it boils down to is, and this is a summary of what Turing said. What Turing said was, you can only have a finite number of mental states because you only have a finite brain. You can only have a finite number of symbols because if you had an infinite number of symbols, you wouldn't even be able to tell them apart. You know, they would be infinitely close. Any successive pair of symbols would be infinitely close to each other. You couldn't tell them apart. So you wouldn't be able to reason with them. And also, the amount of information you can have under investigation at one time also has to be finite because, let's face it, you can't look at a string of 12 nines and a string of 13 nines and tell them apart at a glance either. So Turing lays down what today we, of course, recognize as the definition of an algorithm. What is an algorithm? It's a process by which you look at data in a finite number of steps in finite time. That's the definition of an algorithm. You can process things in a finite number of discrete steps in finite time. And so I'll argue that Turing's definition, all these definitions, Church's, Turing's, Gödel's, they're all constructive by default. They might not have been described as constructive, but they are. They reflect this old pre-Cantor 19th century idea as to how computation works. Okay, so if you reject the law of the excluded middle, P or not P, you reject double negation implies the positive, not P implies P. How do you actually reason with that? I mean, doesn't that, something else that Emily alluded to is that poses real problems for calculus, for example. But it turns out that people have actually taken this ball and run with it, and they've come up with things like smooth infinitesimal analysis. Another sidebar, here we go. It's for anybody who's even been in college over the past 20, 30 years, 40 years, if you study physics and you study calculus as separate subjects, one's in the physics department, one's in the mathematics department, you can't help but have noticed that the same math, calculus, is taught two completely different ways. In the physics class, you'll be dealing with infinitesimals, and taking them to higher powers means you get to cancel out those terms, and differential calculus in particular becomes much, much, much simpler. In your math class, you'll be told that infinitesimals are logically unsound. They were banished at the end of the 19th century by Weierstrass and Cauchy and those guys. And you must use limits, and you must use epsilon delta proofs if you want to prove that anything is actually true. So books like this take us back to infinitesimals, but they found them on constructivist logic, and guess what? It turns out there's a definition of the real line constructively in these terms, in which all functions on the real line are continuous. They're all infinitely differentiable. You don't have to worry about, can I even differentiate this function or not? The answer is yes, you can. And you get to use infinitesimals. You get to do the simple way. You get to do the easy way, where differential calculus reduces to algebra. Any infinitesimal that's squared or taken to a higher power goes away completely. It dramatically simplifies. I'm pissed off, to be honest, because I didn't get to learn this when I studied physics for however many years. I had to learn it the hard way. I had to learn it with a whole bunch of nonsense about, well, what about functions that can't be differentiated? What about non-continuous functions? There are none. Okay, that's the kind of nonsense that persists in math today. If you go study math today, you will be taught that nonsense. Yes, I'm angry. What's the benefit? Yeah, I sort of already covered this. Applications become simpler, all functions are continuous and infinitely differentiable, and integral calculus is just anti-differentiation, and everything becomes, and importantly, having talked about how awful the Banach-Tarski paradox is, you can't prove Banach-Tarski in this system. It's not a theorem in this system. You can't get there from here. Why? Because this system rejects nonsense like Banach-Tarski, right? That's the point of constructivism. The point of constructivism is to say, you can't assume that you have information you don't have. P or not P is not accepted. You have to have a concrete algorithm. You have to have a step-by-step process for P, or to show that P implies a contradiction. P implies falsum. P implies bottom. In Scala, it would be a function definition that takes an argument and the return type is nothing, for those of you who know Scala. What did that just mean, right? How many people have heard of the Curry-Howard isomorphism? Yeah, a couple, okay. So it turns out that in constructivist logic, there is a one-to-one correspondence between a program and a proof. A program is a proof. A type is a proposition being proved by the program that has that type signature, right? And that's the basis for these proof assistants and even programming languages like Hawk and Inverse, both of which are based on a type system that is a good one for taking advantage of this Curry-Howard isomorphism. And that's a sidebar that, We could go off forever and ever and ever just on that. But I want to continue on the main path. Algebras. We talk about algebra. We talk about algebras. We talked a little bit about algebras as such. I want to go back to physics a little bit. I want to go back to the end of the 19th century, where it was recognized by this guy in particular. This is William Kingdon Clifford, who actually took advantage of a couple of other physicists' work, Hamilton and Lagrange. Hamilton, in particular, his solution to the problem of Newtonian mechanics requires you to literally specify all the forces that interact on every point in space, in an object. You know, what's the motion of this object going to be? Well, the motion of this particle is going to be that. The motion of this particle is going to be that. You can't actually do physics that way. So Hamilton figured out how to do equations of motion for whole bodies. One of the things he was really concerned about was rotation, right? Rotation in 3 dimensions. This turns out to be a hard problem. There was another Swiss mathematician back in the 17th century, Leonhard Euler. By the way, it's pronounced Euler, not Euler. That's what I get for being a German speaker. Euler came up with this notion of a way of describing angles. They're called Euler angles. And you can describe rotation with them, but don't, because you will kill people that way. And I mean that literally. If you're designing a jet, a military, fighter jet or whatever, and you use Euler angles and you use the algebra that you use to describe rotations with Euler angles, you run into a problem that's equivalent to division by 0. It's called gimbal lock. And it basically happens when 2 of the 3 axes coincide, when they're oriented in parallel to each other. You lose a degree of freedom in the equations at that point, and you get, the technical term is singularities. You call it division by 0, infinities, whatever. And your plane crashes and the pilot's dead and everybody gets very unhappy. So fast forward back again to Hamilton. And Hamilton comes up with a new description of 3D rotation and an algebra for it. And this is called the quaternion algebra. And it's interesting because Hamilton takes years. He thinks about this problem for years. He's got an algebra in mind. And it's got 3 terms. Why 3 terms? Because Hamilton is a devout Christian and he's very impressed by the fact that space seems to be 3D, and he's interested in the Trinity. He thinks that actually is expressed in physical reality. And he thinks that it takes 3 terms to describe rotations completely in 3 dimensions. I use this as an example of how your faith can lead you astray. And I am a person of faith. But your faith can lead you astray. So the reason he wandered around literally for years beating his head against this problem is because you actually need 4 terms. And he finally figured this out in a flash of insight as he was walking with his wife across a bridge in Ireland. He was Irish. He was walking across this bridge with his wife, nice sunny day, thinking about this problem for the 7th, 8th year. And finally has this flash of insight that if he adds this particular term and it satisfies these particular laws, then his algebra has what's called the closure property. And this is something that John actually talked about when he talked about compositionality. This is what the closure property, and that's a formal term from algebra, from abstract algebra. The closure property says, given an element of your algebra, if you perform some operation on it and get another of that same type of entity in your algebra, if you add 2 plus 2, you start with an integer, you add another integer, you get another integer, right? Then your algebra has this closure property. This is very important because what do you get if you don't have the closure property? Who knows, right? The short answer is nothing. You get divergence, you get infinities, you get division. This is division by 0. Division is division in the natural numbers, the integers, real numbers, whatever. Division is not closed. The division operation is not closed in the presence of 0 in the denominator, right? What is anything divided by 0? There is no answer to that question, right? This is the problem that Hamilton faced with his quaternion algebra until he added the 4th term, and then all of a sudden he discovered that he had a closed algebra. You could put a quaternion in, you could perform rotation in 3D on it with operators that he defined, and what do you get out of it? Another quaternion. very big deal for classical physics at the end of the 19th century. And he knew that the lack of closure was a problem, so he worked on it for years. It was not okay to have an algebra that lacked the closure property because you couldn't reason with it. You would get nonsense out of it under certain circumstances. That's not okay. So it's very important when you're designing an algebra to make sure that it has the closure property. So not only is John right, I think he didn't make his point strongly enough, to be honest. It is vital for your algebra to be closed so that you don't get nonsense out of it. And then fast forwarding a little bit to this guy, William Kingdon Clifford, he took the quaternion algebra from Hamilton. He took something called the exterior algebra from Hermann Günther Grassmann, which talks about sort of the exterior algebra. So basically, how do you describe the combination of sort of things that are not going in the same, they're perpendicular to each other. So this is all about geometry, but it's also about how to express geometry algebraically, right? And that's actually what Clifford calls, you might have heard of Clifford algebras, but he called them geometric algebra. His whole point was that there is a one-to-one correspondence between geometry and this algebra. You take the algebra, you can translate it to geometry. You take the geometry, you can translate it to algebra. It's one-to-one, and it always works. And that's really interesting. That's interesting if you are designing a fighter jet. That's interesting if you're developing computer games. Here's a little bit of code, the only code in my entire presentation. I said I wasn't going to talk about functional programming, I lied. This is a little bit of C++. I tried to do some syntax highlighting, but guess what? It doesn't really make much sense to highlight C++ syntax because it's nonsense. But here's a very small C++ snippet. Maybe I should use the pointer, but whatever. Anyway, we define a circle, and a circle is defined by taking the wedge product, is what this is called. See the little hat there, the circumflex? That's called the wedge product. So you define 3 points, and you wedge them together with the wedge product to get a circle. And then, what do we have? We have a sphere, is it? Yeah. We define a sphere, and we want to know where the intersection of this sphere, of this circle and this sphere is. And if they do intersect at all, it's going to result in 2 points. Right? So that's just neat. All it is. How hard is it to take the intersection of a sphere and a circle in geometric algebra? It takes about, 3 lines, 4 lines? And then you wind up with this thing, which is a representation of these 2 points where the circle and sphere intersect. And you can actually draw that. It's executable. You can run this program. You can compile it and run this program. By the way, the library is called Versor, V-E-R-S-O-R. Versor is a central construct in geometric algebra. It turns out that this wedge product and meet and all that kind of stuff, those are all actually special cases of one thing, which is called the geometric product. And that's it. There is one geometric product in geometric algebra that does everything. These are just convenience methods or convenience functions wrapped around that so that you can talk about things that are convenient to talk about, that you want to be able to talk about easily. And it's really interesting, I should mention too, talking about orthogonality. In geometric algebra, this fascinates me. In geometric algebra, the geometric product, let me back up a step. In geometric algebra, you can treat an arbitrary number of dimensions. Doesn't matter. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 500, 5,000, we don't care. So it's a graded algebra. And it turns out that the geometric product is a grade-raising operation. If you take the geometric product of a 2-dimensional thing with a 1-dimensional thing, you get a 3-dimensional thing. And the dot product or inner product is a grade-lowering operation. It projects n dimensions onto n minus 1 dimensions. So that's, I think, as rigorous a definition of orthogonality as you can get. You know exactly what is going to expand your number of dimensions, your degrees of freedom, and you know exactly what is going to reduce them. And it's executable. You can run this on a computer. Okay. So that's a long sidebar talking about the benefits of constructivism in calculus and in geometry. Let's get back to a little closer to home as far as information is concerned. Ray Solomanoff, so 1965, Ray Solomanoff takes this whole stew that E.T. James had really sort of gotten the ball running with respect to the relationship between probability theory and information theory. And if you're familiar with Bayes' theorem, you know that it tells you how to update a probability that you already have based on new information. Great. The question, of course, burning with respect to Bayesianism is, how do you come up with that initial probability, right? Where does that come from? Ray Solomanoff came up with an answer to this. He came up with a universal probability distribution that applies everywhere to everything. And then you can plug that into Bayes' theorem and off you go. There's an interesting description. What he's trying to do is he's trying to talk about learning. He's trying to talk about what to do when you acquire new information and how to say, I know something as a consequence of this. Or, I have good reason to believe, it's a probability. I have good reason to believe this. And he says, basically, all computable theories which perfectly describe previous observations are used to calculate the probability of the next observation with more weight given to the shorter computable theories. So basically, if you have a function, you have a program that calculates given data, generates results that are consistent with some theory, with some scientific theory that you have, then when you get new information, what new calculation or what new reasoning process should you attribute, or should you choose to add to your theory, basically? And the answer is the shortest one. The shortest computable one. They do need to be computable. Again, we're trying to avoid talking nonsense here, right? So they do need to be computable. And the problem with this is that Solomanoff's universal prior is only semi-computable. You can only approximate it from below. You can't actually compute it outright. It turns out, and it's been proven at this point, that Jane's approach to coming up with prior probabilities before plugging them into Bayes' theorem is a special case of Solomanoff's universal prior. It's called maximum entropy. And you can do this. Physicists know how to do this. They've known how to do this for years and years and years and years. Given a function, it's called constrained function optimization, and the way you do that is you apply what's called a Lagrange multiplier to the function to express the constraints on that function, and then there's a rigorous mathematical process to optimize that function. And that's how Janes, it's one of three ways that Janes likes to come up with prior probabilities, and it's like it works. It assumes the least about the data that you're analyzing. It doesn't assume information you don't have. That's what maximum entropy means. Don't assume information you don't have. And then again, Janes says, by the way, you have to do math the old way. You have to do math the pre-Cantor way. Solomanoff says essentially the same thing. Learning is information compression, yeah. Some of you may have heard of a principle called Occam's razor. The simplest explanation is the most likely to be true. That's essentially what Solomanoff just said, except he said the shortest algorithm that gives you the same results as your existing theory is the algorithm you should use. You should use the shortest one. The other factor that is significant to that is the number of results you get from the shortest computable theory. And David McKay here wrote a whole textbook, which I highly recommend, about learning algorithms and information theory. And it's basically about machine learning using these principles, using this principle of the shortest program that gives you the same results as your existing theory, given new information, is the one you should prefer. And makes the point that learning is information compression. There's really no simpler way to put it. It is equivalent to data compression. If you have a file and it's a certain size, and your compressor, your file compressor, can compress it down to a certain size, that means that there was a fair amount of redundancy, there was a fair amount of entropy in that original file. The actual information content of that file is smaller. I'm assuming lossless compression here. What lossy compression does, of course, is say, we have some sort of mathematical model of what you're going to do with this data. In particular, you're going to listen to this music, right? Or you're going to watch this video. We can afford to throw away a certain amount of that data because we know how the ear works. We know how the brain works. We know that well enough that we know how to do this, how to throw away a certain amount of data in such a way that your brain will fill in the blanks. That's literally what happens when you listen to that MP3 or that other lossy compression formats. Much harder to do with video, much harder to do with audio than with video. With video, you can throw away every other frame that we used to in TV before the digital era, right? That's what interlaced means. They would throw away every other one. And it's like, okay, you can still make out that picture fine. Your brain would literally fill in the blanks for you. With audio, it's a lot harder. You can't really throw away just arbitrary chunks of the audio, right? You have to do smarter things. So lossy compression of audio is actually very tricky. But lossless compression is machine learning. To losslessly compress something, you're learning what the information content of that original data is and throwing away the redundancy. And when you decompress it, you're saying, let's bring back the redundancy in this description, and here's all your information. Data and information are not the same thing. So there's this deep relationship between information, what an algorithm is, compression, machine learning, physics. Oh, by the way, I forgot, important point. I said when Shannon came up with information theory, it was in the context of physical communication channels, right? Noisy communication channels, telephones, radios, Can you make out what the other person is saying at the other end of the line? Quantum mechanics, just to circle back there for just a second, quantum mechanics tells us a lot of things. One of the things it tells us is that information in the universe is never lost. This is called the unitarity principle. If you look at it in terms of Schrödinger's equation and Born's interpretation and the probability of the wave collapse having a particular result and all that sort of thing, all it means is that all the probabilities sum up to 1. Something does actually happen. All the probabilities sum up to 1. So information is never lost in the universe. That is a bedrock principle of quantum mechanics. It was so important that it resulted in a big schism between the recently late Stephen Hawking and some other physicists about what happens around black holes. When things go into black holes, does that information actually disappear? All that kind of stuff. And that resulted in a book called The Black Hole War by Susskind, the other side of that argument, and I highly recommend that. Anyway, there are 6 or 7 different interpretations of quantum mechanics. They all agree on one thing and one thing only. Information is never lost in the universe. Okay. Isn't one of the implications of that when you flip a bit in memory, that the old bit value has to go somewhere? Right? If information is never lost in the universe, what happens when you flip a bit in memory? Where does the old information go if information is never lost in the universe? It gets dispersed as waste heat. This result was established also in 1965, but it wasn't actually demonstrated, it wasn't proven to be true until 2012. But it turns out it is true. We can actually calculate the minimum amount of waste heat that will be lost when you change a 0 to a 1 or a 1 to a 0 in one bit of memory. So it turns out that all this information theory stuff and all this physics stuff and quantum mechanics stuff and all that kind of stuff turns out to have a direct bearing on how computing hardware works, and in particular on how computing hardware doesn't work. Right? And what I mean by that is you can't continue to make circuits smaller and smaller and smaller and smaller and faster and faster and faster and faster because, of course, they generate more waste heat as you continue down that road. And that is a current problem. If you talk to any engineer at Intel or ARM or anybody else who designs CPUs, they'll tell you, it's like, okay, we're getting to the end of the physical road here. By 2050, we won't be able to do this anymore. We won't be able to make the circuit smaller until we figure out how to solve the waste heat problem. What's interesting about that is that we know how to solve the waste heat problem in designing these physical circuits, which is, don't throw away the old information, right? That's what's happening. That's what waste heat is. You're throwing away the old information that was there before you changed it to the new information. And what that implies is we have to design what are called reversible computing circuits. We have to make circuits so that when you put in the new information, the old information comes out some other pin. on the chip, right? And then you have to send it someplace else and yada, yada, yada. And I don't know how you solve that problem globally. But reversible computing hardware means that you don't lose the information to waste heat, you just get it out of some other pin on the chip, right? Doesn't that sound like a purely functional chip? So the next time some yo-yo tells you that hardware is imperative, they're wrong. Hardware only seems imperative because of the side effect, the literal side effect of waste heat, right? That is the only reason your computing hardware looks imperative, is because of side effects. What side effect? Waste heat. So, what's another point I want to make before we wrap this up? There are a bunch of complicated problems in the world right now. General relativity and quantum mechanics are mutually incompatible. They can't both be true. Our two best physical theories in science can't both be true at the same time. If you take Einstein's field equations of general relativity and Schrödinger's equation from quantum mechanics and you plug them into each other, you get nonsense. You get infinities, you get divisions by zero, you get singularities, they don't work together. The universe, you might have noticed, couldn't care less. Right? Seems to be trucking along just fine you can use general relativity like some of my former colleagues who work at JPL did to control unmanned spacecraft that moved fast enough that they had to take relativity into account to make sure that their trajectories were correct. Right? There's a mind bend for you. Yes, I'm programming for a machine that is moving so fast, it's getting fast, close enough to the speed of light that I have to use relativity to figure out how it's going to go, where it's going to go. Quantum mechanics, hugely experimentally verified ever since it was founded in the 1930s. They just don't work together. They're like, bad roommates. So that's one problem. What's another problem? We've sequenced the entire human genome, right? That's an amazing accomplishment. What we haven't done is we haven't figured out how any genome folds up in 3 dimensions to form a protein, or what those proteins do. It's called the tertiary structure problem, or the protein folding problem in molecular biology. Economics, right? We may have noticed, you may have noticed, that there's a horrifying recurring tendency for the financial system to just collapse from time to time, roughly every 8 to 10 years. And that seems to be a recurring phenomenon that you would think we could get some sort of handle on. These are complicated problems. These are sufficiently complicated problems. Here's my real thesis. My real thesis is that these problems are going to be solved by you. What I mean by that is these problems are sufficiently complex that they cannot be solved by unaided human intelligence. It is going to require software assistance to solve these problems. So, what that means is your software can't talk nonsense. The problem with that is classical mathematics, classical logic, classical calculus, classical physics, quantum mechanics, general relativity are all based on nonsense. They are all based on nonsense. They are not based on information. The only way I'm convinced, the reason I'm here, the reason I'm talking to you, I am convinced that the only way forward is on constructivist grounds, is on the grounds that Jaynes uses to make probability work based on Shannon's information theory and constructivist mathematics, even though he doesn't go as far as the smooth infinitesimal analysis folks with respect to how to actually do that. He basically says just ignore Cantor. And if you want machine learning to make sense, you can't make assumptions that don't hold. You can't pretend to have information you don't have. You can't bias your learning algorithm, right? So you have to avoid that. How do you do that? By applying these principles. This is all about not pretending to have information you don't have. That, as far as I'm concerned, is the name of the game. And I'll just wrap up with this. I don't know how well this shows up at this scale, but there's a funny sort of picture of an iceberg, and we have classical mathematics at the top, and then we have increasingly obscure approaches to mathematics going down to, all the way down to, I forget what it says down here, but I think it's the fourth one down. I have trouble reading it myself. But anyway, one of them is degenerate. And that's the one that is basically constructivist in the sense that functional programming and type theory and all that kind of stuff deals with the subject of mathematics and logic and all that sort of stuff. And that's where I stop, so just be degenerate. And I think that's basically, yeah. Closing thoughts. The first one is another one that I really want everybody, if you only take away one thing, this is really it. It's a call to action. This is from the preface of the second edition of Scientific Inference, Sir Harold Jeffreys, which is one of the texts that inspired E.T. James, who wrote Probability Theory of Logical Science. Scientific method can be understood if and only if a theory of epistemological probability is provided. I maintain that much that passes for theory of scientific method is either obscure, useless, or actually misleading. It's nonsense. If it's based on classical logic, if it's based on classical mathematics, it's nonsense. You will get nonsense out of it. There may not even be a problem in physics with respect to general relativity and quantum mechanics. It may not be a physical problem. It may only be a mathematical problem. It may be that the mathematics that's used in those subjects winds up being mutually incompatible because it's nonsense. The math is nonsense, not the physics is nonsense. The math is nonsense. If you read Three Roads to Quantum Gravity, Lee Smolin, he talks about a few newer approaches to quantum gravity, one of which is based on a constructivist mathematical approach, and I have some hope for that. But it's early days yet. It is very early days yet. So my call to action for you is to not pretend to have information you don't in your code, in your thinking, in your mathematics, to the extent that you do any mathematics. Please join the counter-revolution. We need to go back to pre-Cantor 19th century mathematics. We have newer tools to do it. We have some category theoretic tools like topos theory, smooth infinitesimal analysis, geometric algebra, geometric calculus. So the future actually does look fairly bright. But the beginning of the counter-revolution has only occurred within about the past 10 to 15 years. You have the opportunity to participate in this counter-revolution at its early days, and I hope that's what you do. And that, I believe, is all I got. Thank you, everybody.